Okay. We're going to start a little bit earlier today. Welcome to the Optimus Solutions webinar on why perform a finite element analysis. For those of you that are watching, we do have our webcams on so you guys can see us, and again, we have the drum sitting there because we're going to chat with each other. We're going to talk through some of these details. If you can't see that, then feel free to listen. My name is Tom Zhang. I'm the Senior Engineer for Optimus Solutions. What we're going to do here today is I would like to introduce to you guys a brilliant engineer in our group, Cephas Idan, right? Idan. I'm so sorry, Cephas. Cephas does a lot of our finite element analysis work. And what I would be interested in is your background. Cephas has been all over the place. So tell me a little bit more about that.
So my journey actually started in Ghana.
Right.
I had my bachelor's of mechanical engineering.
What got you into doing that?
My interest really was in physics.
Okay.
Now, if you are in Ghana or most African countries, like usually third world countries, you get the advice that don't do theoretical subjects or courses because you don't get a job.
So you did it from an economical standpoint,
exactly.
Huh?
So the closest to physics was mechanical engineering or electrical engineering. So
I see.
Two options that allows me to explore my interests while also engaging in a degree that is applicable to the economic situation.
Okay, so you wanted to be a little bit, you wanted to do the physics, but you're trying to be a little bit more on the practical side on getting a job.
Yes.
Okay.
Because with the physics, you most probably might have to be at the university teaching. Whilst with the mechanical engineering, you could still teach physics,
right?
Or you could teach mechanical engineering modules, or you can work in industry. So it's me more flexibility.
Right.
Yeah.
So how did you end up in England then? Because I mean that's kind of a big leap.
Yes. So after my degree in Ghana, we have what we call the national service. So after your first degree or bachelor's, you're supposed to serve the government for a year.
Like military or just
it's an option. So that was actually my first choice, that I will go into the military.
Right.
But then I got a position at the university as a teaching assistant to do my national service there.
Okay.
So I took that. That was during that time that we had some scholarships available for anyone who wants to pursue further studies.
Right.
There was this PhD program in England with full scholarship and stipend.
That's an easy decision, huh?
Yeah. So that was very easy for me. There were two scholarships, one to Germany and one to England. The Germany was full scholarship but with no stipend, but England was full scholarship for the duration of the PhD and stipend, a monthly stipend. So, and I don't have to learn German.
Yeah, I mean, doing the English, you have a little bit of an English accent. So you got from Ghana to England. So how did you end up in the U.S. then?
So in the U.S., my wife had an opportunity. So basically from England, after my PhD, I went back to Ghana to the university, went to teach at the mechanical engineering department. And then my wife came to the U.S. and she liked the U.S. So I was shuttling between U.S. and Ghana, but then I realized that I just have to bite the bullet and move to the U.S. So that's how I found myself in the United States.
So then your journey from Ghana, then to England, then to U.S. So how did you end up doing some of the initial FEA work or some of the initial, mechanical engineering work?
Okay. So one of the modules that I was actually teaching in Ghana at the master's level and the bachelor's level was CAD-CAM. That was the name of the module.
CAD-CAM, okay.
So it's split into two. Part of it was actually simply 3D modeling.
Right.
And the other part was more of computer-aided engineering. So even though we call it CAD chromosomes more of computer-aided engineering, where we have CNC, which basically forms the manufacturing part, and finite element modeling or finite element analysis. So we were using tools like ANSYS for the FEA. But I was teaching the FEA.
Right.
We start from the basics, using the direct stiffness method for calculating the FEA for simple structures like trusses.
Right.
And then when we move to ANSYS, we use the APDL for some of the simulation, and then we also use a workbench in ANSYS for some of the. So I started in Ghana.
That's a lot. So you started teaching this in a sense. Well, cool. Hopefully, it's a unique enough journey that I just want to share that with the group out there. Okay, so we're doing finite element analysis on rotary equipment, and I would say we kind of ended up doing this because we kept getting more and more questions. So why don't you expand a little bit about that on the first bullet over there on some of the problems we ran into, why we do this, and what are some of the projects that we've been working on?
Yeah. So in US, actually worked with a company that manufactures oil equipment, for the oil industry. So that's where I had more extensive use of FEA.
Right.
And when I moved to Optimus, we realized that most of the questions that we get, the answer to those questions are what we call rule of thumb, or some of them might be empirical equations, which are based on certain conditions which do not necessarily apply to the unique circumstances of the client.
I see. So it's more of a generalized either equations or empirical data or rules of thumb that, hey, it's about an inch, you should use that. That's what the industry uses.
Correct. Yeah. So you can see that applying the same principle to a particular client's need does not necessarily solve their problem. It's unique. And
so then this is more like originally it was more like a one-size-fits-all, and then now it's a little bit more custom to that particular problem.
Yes. So some of the problems you can easily solve with classical mechanical equations or classical equations, but looking at the rotary equipment, it's very complex with very complex loading scenario.
Moving, it's not always directly in the center.
Exactly.
It's long, it's hot. It seems simple. It's a rotating cylinder, but when you get into the details, it's not so simple.
That's simple, yes. So FEA has been found to work very well when we are dealing with complex situations. So why not adapt it to the rotary industry?
Absolutely.
And we started with in-house projects where basically initial design, where if we are designing maybe a gear cover, we want to know how stable it is. So that's what we started with, and then gradually we moved into other areas depending on the client's needs.
I see. That's pretty interesting. So overall, I mean, it's I feel like it's become a pretty good capability that we have. I do know that some of the questions that are, say, maybe industry standards, like, for example, some misalignments that have a rule of thumb is 3 millimeters or 1/8 of an inch, we're actually starting to tackle these rules of thumb in the industry with this tool and this technology now.
Yes.
I mean, we'll show you guys some of the details of that because we do want to share some of the neat concepts that we've been working on. But let's talk about some of the projects. So tell me a little bit about this one. I remember you had a lot of details that you wanted to discuss on it. So kind of phrase the problem itself.
Okay. So this was from a client who was having a problem with his funnels.
Okay.
The shafts keep breaking.
Okay. And breaking as in, say, here at this area, or breaking overall, or just in general?
This basically snaps into two around where you have the edge, the roller and the shaft interface.
I see.
And it's not very clear in the diagram, but some design modifications have been done on the roller to give some stress relief, because the initial thought was, since you have a notch in there, then you're going to have a stress concentration in that area.
Right.
So that was why they made those design changes. But in spite of those changes, the shafts keep breaking. They went through several iterations in terms of materials, but it's still the same problem persisting.
Right.
So the next phase was, okay, why don't we run this through an FEA, since that might give us an insight of what exactly is going on.
Right.
Because based on all our calculations, it should work. So why is it not working?
Right.
But the thing is, all the calculations we did assume perfect scenarios.
I see.
You can't really tell the flow of stress around these. You can use the equations and you get some values, but with FEA allows you to actually see how the stress varies across the whole spectrum of the shaft itself. So that's what we did, and we realized that the stresses are very high at that edge.
Right, at edge between the shaft and the roller.
And the roller
connection somewhere here. So let's see if I can do a little drawing to show that. Let's do this. So somewhere here. Oh, no. Here. Let's see here.
Yes.
Okay.
Now the other aspect was that this is basically two components fitted together, and we're using an FN3 shrink fit.
Right.
So with no load on the roller, there's already a concentrated a compression force on the shaft.
Right.
So even without any load, there's load on the shaft.
Right.
Adds to the initial stress state.
I see.
So any changes in the loading of the dryer, which might not have been accounted for, causes a high stress, which inadvertently leads to the failure of this.
So with the FEA, you were able to get a little bit finer resolution on why, and a little bit, I guess, better visibility on where some of the other stresses are coming in from. Okay, well, cool.
So finally, we proposed that, okay, I mean, why don't we have a system, instead of having a shaft and a shrink fit, have one component. So the trunnion and the shaft should be one component.
Oh, I see. Well, that's interesting.
So that's
cool. Well, let me delete this right here. So we talked a little bit about that. So this is the tire and tire pad analysis. So this one, I'm pretty familiar with that, where the customer had an X amount of pads. And then we were like, hey, what happens if we decrease, let's say half the amount of pads, and made it wider? So tell me a little bit more about this particular analysis. I think you had some headaches on this one.
Yes. So basically, I think initially they started with a unique system of parts. They had this wedge.
The wedge. The wedge pad.
And then they had these dowel pins.
Yes.
Yeah. to stop the creep.
So it went from a wedge pad design to a floating pad design.
Yes. And the problem they were having was they had, well, since they changed the floating, there was creep, and they started having longitudinal cracks on the shell.
I see.
So one of the rule of thumb that we use is to have at least 60%, I think 68%, 60 to 68% coverage of pads.
Tire pad coverage, yes.
Exactly.
Yes.
But so that was what we designed this with. So we had a very, in fact, the idea was that if we increase even the coverage, that might help with the cracks.
Right. So the rule of thumb is the more covers, the better.
Yes.
I see. So what did we find out on that?
We read that's not necessarily so.
And so the more pads, so it's almost like an optimal point.
Yes.
So what did we learn on the when there's a whole bunch on the shell? I think it was some related to shell, right?
Yes. So you see, the pads themselves, especially with floating, also have weight. So they could contribute to the flexing at the top. If you look at the results there, you can see that you can clearly see the gap at the top.
I see.
So now this, as it moves up and down, could cause stress variation, which basically could lead to fatigue, especially around where the pads are welded.
Right.
And that was exactly where we were having those cracks. So the thinking here is that the tire might not be thick enough to support the shell. Or we can also reduce the number of pads and then make them wider.
So you're saying that when we did the analysis, we think the tire may be too thin to where it's not stiffening it.
Yes.
Or that we can widen it to not flex so, I guess,
so much.
So
the
much.
Deflection is not that large.
Intense, in a sense? I see. So ultimately, we ended up making the tire thicker.
Yes.
Made the pads wider.
Wider and reduced the number.
And reduced the number. So, and I think that is probably one of those things that you really can't do without doing an FEA analysis on it. I mean, this one was really neat in the sense that we started with more of a generalized project, like, hey, let's look at the loads on it. Let's look at the details of the just a simple load study. But then it evolved into this pretty complex engineering problem. I think, what was it, like 6 weeks?
Yeah.
6 weeks, because we even added on top of that something else where, okay, we made the tire thinner or made the tire thicker, then can we make the roller thinner? Because you can't, it wouldn't align with the whole system.
Yes.
So this one was a pretty neat project, I think.
Because we wanted to maintain the slope of the system.
Yes.
And to do that was either to shim one end if we increase the thickness of the tire,
right,
or reduce the roller size so that the center of the tire remains the same.
Cool.
So those were the two options to maintain the slope.
Cool. Tell me about this one.
So this was based more of an initial design.
Right.
And the customers, the client's concern was to ensure that the dryer is structurally sound and will be able to endure the stress variations that it will be going through. So this was more of an initial design. So it's a whole dryer FEA where we looked at the stresses on the pipe support and the interface between the pipe support and the shell itself.
Right.
The stresses in the shell itself, and these have to be below a certain value. Based on the client, we were using the BS, I think 7906 standard for the fatigue.
That's a British standard, right?
Okay. Standard. It's very well known for fatigue design.
Cool. So this one ultimately ended up being okay?
Yes. Yes.
Because this was ultimately a new unit, and they had our input on helping them determine if this was okay. and then they proceeded to buy the unit.
Because the initial thinking was, okay, if it's not okay, then they might install stiffening
Rings, yes.
to stabilize it.
And that's a really common issue for steam tube dryers.
Yes. But the initial, when we ran it, we realized that the stresses were way below the fatigue stress, allowable fatigue stress.
It's pretty interesting. Okay, so we talked about some of the projects. We talked about some of your background. We've talked about why we ended up doing these types of FEAs. So what are some of the headaches you've ran into?
Okay. So the easiest, especially if you come from an academic background, is to continue analyze because you have the tools at your disposal.
Right. It's normally a big engineering problem.
Yes.
Analysis paralysis. Huh?
Yeah. So if you're not very careful, you fall into that scenario.
Delay in the project.
Yes. So you always have to know when to stop that. Okay, this is refined enough, and the answers you get, the more you refine, the more accurate you get. But then the difference is not that much. That it's practically significant.
Right.
So you need to be able to catch yourself. That, okay,
right.
This is enough for practical purposes.
Well, and also you have a time limit.
Yes.
Because if we are working on that, I mean, if we say, hey, this is a 4-week thing, and then it ended up being an 8-week thing because we just wanted to get that extra 1%.
Yeah.
We have to define if that 1% matters. And if you're at 99% and this is 98%, is that good enough?
Yes.
I see. So I think this one is one of those where if we get a very defined scope up front, hey, if you do this, this is what it is, then I think that helps. And I guess the way we help with this is answer the question.
Yeah.
Right?
Yeah. The other area too is most of the packages that we use as of now, we use Autodesk Nastran and SolidWorks simulation.
Right.
Yeah. Now, one of the challenges here is meshing.
Tell me a little bit more about what meshing is.
So,
I guess there's a picture back here. This would be a mesh on the right.
Yes, that's a very fine mesh for that side.
Right.
Now, the whole idea of FEA is to take a homogeneous structure or a continuum and break it into smaller pieces. Okay.
Right.
Now, these smaller pieces are what we call the elements, and they are joined at points that we call nodes. Okay. So the idea is take a geometrically complex figure where you can't really calculate force over area to get your stress.
Right.
But when you have these small elements,
it's squares and rectangles.
Yes, or tetrahedrons that you can use differential equations, which you can also turn into matrices for the computer to solve those equations for you.
What we're doing is we're taking a complex structure, we're making it small enough that you're getting squares and shapes that are easy to calculate, and instead of us calculating 1 million or 1 billion equations, we're having a computer do it.
Exactly.
Okay.
Exactly. So in the past, we realized, okay, computers are very good in matrix calculations. So we turn these equations into the form of matrices, and you can use several methods. The easiest would be to find the inverse of the matrix, but that doesn't really happen.
Right.
Yes, we normally use Gaussian solutions. That's the direct method, or we use iterative methods to solve these.
And those will change your computational times typically.
Yes. So the process of breaking this structure into tiny pieces is what we call the meshing.
I see.
Now, where the problem lies in meshing is the smaller your mesh is, and I say this in quotes, the more accurate your results will be.
Right.
Okay. Now, the reason why I say this with a caveat is that we also have the problem of singularity.
Yes.
Okay. Where the finer the mesh gets, the higher your stress rises.
Right. Because it's a stress over a force over a very small area. It's like a knife, very high stress.
Yes. So you must be able to differentiate between real stresses and singularities in your FEA.
Right.
Now, the idea is that as the mesh becomes smaller, the stress should rise and then later plateau. And you know that, okay, this solution is resolved.
Right.
Okay. Now, if it doesn't happen, then that means you have a singularity on your hand.
Right, and you got to go back and remesh.
The other aspect is the finer your mesh, the more load you put on your computer. So how much power do you have?
Right.
Let's say you have a problem that doesn't have singularities. So you have to decide that, okay, this mesh is fine enough.
Right.
After I mesh, the change in stress was, say, about 0.1%.
Right.
Okay.
It's good enough.
It's good enough.
Right.
It's resolved.
So when you ultimately end up with boundary condition issues because that's what you call your initial solutions?
Yes. So that some of the boundary conditions will be, how is the equipment held?
Right. Is it fixed?
Is it fixed?
Is it floating?
Yes. Is it welded? What are the interfaces between, especially if you're dealing with assemblies?
Right.
Yeah. How has it been? What are some of the initial conditions?
Right.
And this is where we usually tell clients that it's easier when you employ an FEA house that deals with the type of equipment that you're dealing with, because then those guys or those analysts understand how the equipment operates. You see, so for example, before I started working here, and I don't know much about rotary equipment. If you give me an FEA, I now have to understand how rotary equipment operates. What are some of the nuances?
Right, right.
Then I'll be able to define real or good boundary conditions. Because if your boundary conditions are wrong, you will still get very nice, beautiful results.
But they are wrong. Right. Which is probably why there's still skepticism in the FEA process.
Yes.
Right?
Yeah.
And I would say that's probably something that we try to work towards is we are skeptical of the results too. Yeah. And that's where you have a data set and then you and I go, okay, is this real? Is this not real? And then we cross-compare with someone that's been in the industry for a while. So, hey, man, do you normally see this crack here? Or do you normally have this issue here? Yeah. And then as we get all that information in, then it's a very clean solution with a lot of the experience to back it up, yes. I think.
And it's nice that you mentioned about this skepticism. If you go back to the roller diagram, we didn't really need, we're not interested in the bearings, okay? But to give the client some confidence, we decided to model the bearings as spherical bearings so that the initial condition of the roller is the shaft is embedded in a spherical bearing.
Oh,
it's a realistic condition of how
it's almost like a double check.
Exactly. So that way, that gave the client some confidence that, okay, this is going to behave as close to the real world situation as it can be.
I see. So we talked a little bit about the FEA in terms of just the projects themselves. One of the things we've done is we have load studies that we do, and these are the Hertz pressures. In the industry, it's very common. I see it all the time. But what I haven't seen is an integration with FEA. And what I mean by the integration with the FEA is to model it with the right load where we have that data. But how can we put a deflection on it? How can we put a misalignment on it? Tell me a little bit more about that.
Okay. So, I mean, as you mentioned, this basically came from discussions where if there's a misalignment from what are some of the effects it has on the shell stress? Because for example, when we do the standard load study, we assume that there's no deflection.
Yes, it's perfectly aligned.
Yeah, there's no misalignment. And also, we use the beam method, which basically doesn't take into consideration some of the nuances or some of the uniqueness of a kiln. So, one of the new things that we've been doing is when we have a kiln access survey data, we are able to input the deflections in an FEA model on the kiln, and we can calculate or we can simulate the stresses that are generated in the shell, and we'll be able to better advise as to how the fatigue is going to affect the lifespan of the shell. We can tell you how much stress is being generated.
And I would say this particular one, we did talk to the client. We did this on our own because this has been bothering me for years.
Yeah.
And the reds on that figure are where we predict high stresses. And ultimately, the client said that there are cracks there after the fact.
Yeah.
So that gives us confidence in the sense that it's not garbage in, garbage out. The assumptions we're making are good, the meshing we're doing is good, the boundary conditions and the experience that we want to verify a real world case is good. So I think that gives credence to the methodology, and it gives credence, and I give you a lot of credit for doing a very good job considering things like that.
And it's quite refreshing because usually one of the steps that we use in FEA is even after the FEA, we're supposed to validate.
Yes.
And sometimes, I mean, for a kiln, validating it means having another kiln and basically running it. But
typically not practical.
Was validated for us free of charge.
Right, because there was a crack in it anyway, right?
Yeah. So
right.
It was. I mean, it's unfortunate for the client, but it also gave some validation too.
Right, the data made sense. Yes. Sadly, you know, I always call it, wow, that's fantastic, but, you know, in reality, it's typically not so good. Okay, well, overall, for the people listening, if you have some questions, you can go ahead and type it into the question set. We have a team that will either answer your questions or work with you guys in asking those. If you have deeper questions that goes beyond the scope of this discussion that we've had, this interview that we had, www.optimusps.com, 502-515-5822, or email us at info@optimusps.com. Our motto is we are focused on the science behind the process. As you guys, or at least I hope that we've communicated, we've been very focused on the science behind the process. I'm going to give about 20 seconds to see if there's any questions that flow in or so. Let's see here. So what's some of the next steps that you think I'm kind of dreamweaving now. What's something that you would like to work on next? That's kind of interesting. Oh, you know, we do have this project on the.
That was what I.
Oh yeah, tell me about that.
So basically, we want to see if we can come out with some dimensionless numbers between the diameters, the length. Because one thing too is we usually talk about if misalignment is within a certain number, then you need to align. But we have to face, I mean, physically speaking, the stress that will be on a particular system is dependent on both the diameter and also the spaces between
the number of piers, the spans, the size.
Yeah. So if you have a short span and you have a deflection of, say, X amount, that's going to be completely different from a longer span with the same deflection.
I see. Well, you know, sounds like we're going to have an IDAN number coming in, and dimensionless IDAN number. But overall, you know, we're here to help, especially during this time. You guys are doing what you need to do to stay safe, stay healthy, and to stay sane. With that, we appreciate you guys listening to us. I know there's a lot of our customers are essential businesses. We're an essential business, especially with the current state in the world. We want to do everything we could to help support every industry out there for the people in need. So again, stay safe, stay healthy, and stay sane. Appreciate it, guys. Thank you.